Dear students, let us continue with our discussion. In the just previous session, we considered how to represent a TS diagram for a refrigeration system when we were using a working fluid such as a refrigerant, which will be boiling or evaporating during the refrigeration process, that is during Part 2, and which will be condensing during the heat rejection process at the condenser. So this will be the TS diagram for such a system. So we were happy that at least we could represent the TS diagram of a refrigerator or a practical refrigerator, at least in the rectangular shape in the TS diagram. But when we look at this TS diagram, it will be clear to us that is 4:1. It is not much a difficult process because it is a constant pressure heat absorption process, but at the same time it will be appearing like a constant temperature process in the TS diagram. But consider the compression process, that is from 1 to 2. Okay, when we closely observe this TS diagram, we can understand that the compressor the compressor is compressing the compressor which is working from 1 to 2. At the compressor inlet, what will be the nature of the working fluid? Okay, the nature of the working fluid or the refrigerant will be a mix of both liquid and vapor region, because the 1 to 2, here you can see the 1 to 2 process, here it can be considered as a wet compression, because the entire process 1 to 2 is happening during the mixture region, or there will be a lot of liquid droplets of the refrigerant or the working fluid which will be existing throughout the compression process. So imagine a compressor which is admitting a mixture of both a liquid and vapor refrigerant inside the compression cylinder. So what will happen? There will be a lot of droplets of liquid refrigerant will be present. Okay, but what will happen to the liquid refrigerant? The liquids, we normally consider them as incompressible fluids. So the liquid refrigerants will be damaging the valve or the cylinder head. Okay, so here during 1 to 2 we are considering the compressor work. Okay, so for simplicity purpose we can consider the compressor working as a piston cylinder arrangement. Okay, so if there is any liquid particles, droplets of the refrigerant is present inside the compressor cylinder, it will be damaging the valve or it will be damaging the cylinder head itself, because normally we consider liquids as incompressible fluids. Okay, there is also another damage, another danger, that is this liquid refrigerant may wash away the lubricating oil from the cylinder walls, which if the lubricating oils are removed, it will cause a great amount of wear and tear between the piston and the side walls of the cylinder or the cylinder liner. Okay, so if this wet compression, that is from 1 to 2, just like in this figure, it is not practically possible, or it will cause a very large amount of difficulty if we are implementing in a practical case. So that is why we are considering another option called as dry compression. So here we are considering our discussion like wet compression versus dry compression. What is meant by this wet compression? Wet compression is shown over here, that is at the inlet of the compressor, some liquid as well as some vapor particles of the refrigerant will be entering it, and this much damages can be caused to the compressor cylinder. Okay, so the working life, the life of the compressor cylinder, valves, piston, etc. will be reduced. So if we are going for a wet compression, so now let us consider a dry compression. All these difficulties associated with this wet compression are happening because the point 1 is inside the wet region or the mixture region. Suppose the point 1 is shifted to the saturated vapor line. So you can see over here, this is the saturated vapor line over here, and this is the saturated liquid line, and at the top we can have a critical point. Okay, so suppose the point 1 is shifted towards the saturated vapor region. So that is, so if the refrigerant is entering the compressor in saturated vapor, then there is no problem. Okay, that is, if the point 1 was shifted to the saturated vapor line, what would have been the advantage? Almost all the refrigerant or the working fluid entering the compressor will be in a vapor state. So there is no presence of liquid refrigerant, and the associated damages which is caused by the liquid refrigerant can be avoided. So such a case is assumed over here, that is by using dry compression. So revision. So here we are revising the earlier diagram by introducing a dry compression. So that is given over here using the dry compression. So what is meant by this dry compression? So again we are considering this TS diagram. We are shifting the point 1 towards the saturated vapor line. So point 1 means the inlet of the compressor. So we are assuming that we are assuming that the almost all or 100% of the refrigerant molecules are now in vapor state when it is entering the compressor. So the compressor now can compress the vapor form of the refrigerant. So this vapor form of particles, they are easily compressible comparing it with the liquid state. So here, since no liquid is present inside the compressor, it can easily compress the vapor form of the refrigerant and finally reaching a point 2. So, but what is happening here? Since the compressor is acting especially on the vapor form of the refrigerant, the compression will be extended to a very large, at the end of the compression, the temperature of the refrigerant will be increasing to a very large value, or it will be entering a superheated state. Okay, so you can see the compression process itself is starting at the saturated vapor state. So again we are supplying energy, or again if we are again compressing the same vapor, it will be slowly transformed to superheated state. So comparing with the earlier diagram like this, so if we are going for a dry compression for 1 to 2, an additional area like this shaded area can be achieved, can be obtained over here, and this area is called as superheat horn. So it is resembling a horn of an animal, a wild animal. Okay, so a superheat horn is the additional energy required by the compressor for compressing the already saturated vapor and transforming it into the superheated vapor state. Okay, so the other processes are remaining same. That is, the only change happened here is converting this 1 to 2 process, or the compression process, into dry compression. So what will happen at the end of the compression? The point 2 will be attained, or the state of the working fluid after the compression process or the dry compression process will be in a superheated state. Then this it is this superheated vapor of the working fluid or the refrigerant, it is admitted to the heat exchanger. So 2 to 3, here we can see it is a constant pressure line. This constant pressure line, actually it is having the shape in the TS diagram like this. So inside the vapor dome, it will be a horizontal line, because during the phase change it is a horizontal line or a constant temperature process, but outside the vapor dome it will be a inclined line like this. So 2 to 3, it will be a constant pressure heat rejection process. Okay, so similar to what we discussed in our air refrigeration system itself. Okay, then this is the case of wet compression and dry compression. So we prefer dry compression over wet compression. Now let us consider a little bit about this expansion process, or 3 to 4. So when we are representing 3 to 4 like this, it is a isentropic expansion process, or expansion process carried out by a expansion engine or a expansion equipment. Okay, but we are always concerned with cost or expenditure incurred for running a system. So as an engineer, we should always think to bring down the total cost of running an equipment. Okay, so when we consider the usage of an engine for this expansion process, usage of an engine for expansion process is practically not feasible. Why? Because this for running an engine, it itself will be requiring a prime mover, or it will be requiring a energy. Okay, but that much energy is not attained during this expansion process. Okay, also the compressor working during 1 to 2, a very small amount of this compressor work can be supplied by this expansion engine over here. So we are trying to avoid, or we are trying to search for alternatives other than using an engine exclusively for an expansion process. But however, with all this, with all due respect of these things, but we need to reduce the pressure of the liquid in 3 to 4 process. Actually, the pressure of the working fluid is increased to a very large amount by this compressor during 1 to 2, and during 2 to 2-3, actually we are introducing a new point over here, 2-. Okay, 2-3, it is a constant pressure heat rejection process. So whatever pressure is attained by the working fluid after this compression process, it is still there. So during 2-3, the vapor, the superheated vapor form of the refrigerant, it will be slowly transformed into liquid form of the refrigerant, but it will be at a still higher pressure. Okay, so at point 3, the nature of the working fluid will be in liquid, but at the same time it will be having a very high pressure. So if we are admitting that liquid directly to our freezer compartment or the refrigerator or the or our cold room, that is 4 to 1, it will definitely damage that cold room or the freezer compartment itself. So we should however we have to always reduce the pressure of the liquid during 3 to 4. So we can think of an alternative other than using an engine, that is simply establish a throttling device, for example a valve, or a small restriction from 3 to 4. That is, the high pressure liquid refrigerant at 3, it will be going to enter a throttling valve or a throttling device, for example a small constriction valve, which will be suddenly opening and closing and causing a sudden expansion process, and thereby reducing the pressure of the fluid or of the liquid refrigerant from 3 to 4. Neglecting the changes in potential and kinetic energy, because this is only a simple valve operating between 3 to 4, we can consider, that is, we can assume that H3 will be equal to H4, or this 3 to 4 process we can assume it as a isenthalpy process. But a constant enthalpy throttling process is always irreversible, which implies entropy will be increasing. So that is why in the TS diagram, this 3 to 4 process, it will be established, it will be represented as a dotted line, and at the same time the entropy is going to increase during this throttling process or the throttling expansion process. And since this is a irreversible process, we are representing it as a dotted line. So now we have attained a final TS diagram of a refrigeration system with a working fluid which will be boiling during the refrigeration step, that is 4 to 1. 4 to 1 is our refrigeration step, and that same working fluid will be condensing during the heat rejection process, that is 2-3. Okay, this cycle is called as a standard vapor compression cycle. Okay, so the details of this standard vapor compression cycle we will be discussing later.